Okay, so this is where we left off, is percent error. Percent error and percent yield, for some reason, kids always mix them up. It's not a hard thing to do mathematically, but I do want you to get good at remembering which one's which, because you will be asked to do it very frequently in labs as well as on tests. So again, percent error is your results minus what you should have gotten over what you should have gotten, and then multiplied by 100 to turn it to a percentage. We use this in labs to figure out how far off you were, okay? And then percent yield is like how well you did in the lab. So again, it's experimental up here over theoretical down here. These kind of go hand in hand. So let's say you got 95% yield in a lab. Well, that would mean you were off by 5%. So your percent error would be 5%. You were off by 5%. So I'm going to give you some fake numbers right now. So I want you to write them down. I want to say, let's say you use, in a lab, you use, you do a reaction and you get 2.78 in the lab grams. Okay. But in real life, you should have gotten 3.15. So calculate the percent error. So what you actually got, 2.78, minus what you should have gotten, 3.15, divided by what you should have gotten, 3.15. So I don't have a calculator handy, so if someone wants to spit out a number, maybe I could use my phone. Just give me a sec. 2.78 minus 3.15. And then remember, times 100. So 2.78, sorry, minus 3.15, this is tricky. You get negative 0.37 on top. That becomes a 2-digit number in terms of sig figs, right? So that means your answer should have 2 digits. So let's see. So it's going to be 12, right? It's 11.7 something, so 12% error, okay? Because of 2 sig figs. 2 sig figs right here. All right, so you were off by 12%. So that's your experimental or percent error, okay? So what was your yield? So how good did you do? Well, technically, whatever you didn't do wrong, you did good. Now, I forgot, this is negative, and you go, well, how can you have negative percent error? The negative is descriptive. All it means is that you got less product than you should have. Look it, you got 2.78 and you should have had 3.15. So you're 12% lower minus less than what you should have. That's why it's there, okay? All right, so percent yield. So your number goes on top. In the lab, you got 2.78 and you should have gotten 3.15 times 100. So this is this is 3 sig figs. So you'll want to do 3 sig figs. 2.78 divided by 3.15 is 88. Sorry about the 3 sig figs. This ended up being an accident. Okay, so it's off a little bit. So 88% yield, that's pretty good. Well, what's 88 plus 12? Well, it's 100. So yeah, I realize this 0.2 messes everything up, but you got to remember that you rounded this number. It was 11.8, I think. And so 11.8 and 88.2 adds up to 100%. You were 88% good and 12% bad, kind of is how you look at it. Are there any questions before I move on? You can just unmute yourself. All right, here we go. So in 2000, which is before most of you guys were born, well, all of you guys were born, FRQ stands for free response question. It's part of the AP test. You always have a multiple choice and then a written. It means the written part. So in 2000, on problem number 5D, they have a percent error question. So you got a point for doing this. So it says, show the setup for the calculation of the percent error in a student's result if the student obtains a value of 126 grams. Remember, this means per mole for the molar mass when the actual value, this is your true theoretical value, is 120 grams per mole. It says show the setup for the calculations. Well, okay, so this is percent error. So it's 126 minus 120 divided by 120. Now, this is where they're mean. This is not the setup. You are incomplete right here. So if you don't write multiplied by 100, they don't give you the point on this one. This one was worth 1 point because this is part of turning something into a percentage. Now notice they didn't even ask you for the number. They just asked for the setup. So here it is. This is the setup. Boom, done. You just did your first FRQ problem for AP. That's pretty cool. And you know how to do it. So, any questions or can I move on? We good? All right, here we go. Atoms, molecules, and ions. All right, so we're going to do a little bit of history. No, you don't need to memorize dates. This isn't a history class, but you do need to know which scientist gets credited with which thing, okay? So, a very, very, very long time ago, a Greek philosopher pretty much proposed the idea that the atoms were made up of small indivisible particles. Now this is going to be wrong because we do know that atoms can be broken down into smaller parts, but he called these all atomos, which we now call atoms, okay? And then a lot later on, another scientist, Lavoisier, proposed the law of conservation of mass, meaning if you have a certain amount of mass of reactants at the beginning, you better end up with the same amount of mass at the end. Even if they change into different substances, mass can't be created nor destroyed. It can't just appear or just disappear, okay? And then beyond that, Proust discussed the law of constant composition based on mass, meaning water is always H2O. There are 2 hydrogens by mass and an oxygen by mass. And that's constant for water. If it's not, then it's not water. It's something else. It has a different composition. Ammonia always has 1 nitrogen by mass and 3 hydrogens by mass. If you don't have that, it's not ammonia. It's something else. Okay? And then very, very big came the first big atomic theory, and this was by Dalton. So I'm going to go through this. All of these theories, 1 through 5, are his theories. This is everything he came up with. I have a true or false written here because I want you to, we're going to talk about whether the statement that we know now, that we're not in the 1800s, if it's still true or false. Okay? So here we go. Each element is composed of extremely small particles called atoms. That is true. Okay, so we have all elements have atoms of the same element. So a piece of silver has a bunch of silver atoms. Okay, so that was.
Can you write this down?
Well, so if you don't have notes printed, then maybe.
All right, thank
you. So all atoms of a given element are identical. Okay, this was part of his theory. This is false now. We know that now, okay? Now, I know 1800 sounds like a long time ago. It really isn't. It's, in the grand scheme of things, 200 years ago is not that long ago. So they're just learning this stuff then. So the reason that this part of his theory is wrong is why? Who can shout out? Are all carbon atoms identical?
Is it because of the different ions?
Close, not ions, but
isotopes.
Yep, isotopes. Carbon has 3 different isotopes, and those isotopes all have different mass, so they aren't all identical. They're all carbon, but they're not identical, and we'll talk about isotopes later. Number 3 that he came up with the atoms of one element are different from atoms of other elements, meaning a nitrogen atom isn't the same as a hydrogen atom, and a hydrogen atom isn't the same as a carbon atom. This is absolutely true. All atoms are different than other atoms, okay? Number 4, he theorized that atoms of one element cannot be changed into atoms of a different element by chemical reactions. This is true. What he's saying is if you have a chemical reaction going on between carbon and hydrogen and oxygen, in your products, you better see carbon and hydrogen and oxygen. If you see like carbon and hydrogen and bromine, the bromine can't just appear out of nowhere. That makes no sense. So you can't like take carbon, hydrogen, and oxygen and throw them all together and then get bromine out of it. It has to be something that has carbon and hydrogen and oxygen. You can't just turn them into another by general chemical reactions. And then the last one, compounds are formed when atoms of more than one element combined, and they all have this similar kind of numbers of atoms. This is true, right? So hydrogen, or I'm sorry, water is always 2 hydrogens and an oxygen. And if it's not water, it's something else. Like H2O is water. H2O2 is not water, it's hydrogen peroxide. Okay? All right, I'm going to move on. Questions? Okay, so again, after this happened, so we have the atom, right? It's this really small particle. Well, J.J. Thomson is the discoverer of an electron. Okay, that's the biggest thing. He took this tube and he applied a voltage. Okay, a voltage is a stream of particles, right? And he noticed that the voltage moved a certain way. It traveled towards the positive end of this container, meaning the atoms, right, matter, must have some negative charge because they know that negative and positive attract. When he tried to do it from the other end, it wouldn't go. And by go, I mean he had the background where the screen would fluoresce, so he could like visually see the matter, or he could see the fluorescent line which indicated the matter traveling across the screen. So again, he discovered the electron. That's pretty huge because before then, they thought atoms were the smallest particles possible. So now we have a subatomic particle, something even smaller than the atom called an electron. The problem is he discovered the electron, but he then tried to make his model. He was English, so he called it the plum pudding model. And I'm pretty sure plum pudding is like pudding with raisins shoved in it. Those are called the plums. So when he discovered the electron, which was negatively charged, he knew there had to be positive charge somewhere, right? Because the atom would need the positive to balance it out. So while he discovered the electron, his model that he designed of the atom is incorrect. If you look at this, the all of this red stuff would be positive charge everywhere, like all over the atom, and the electrons are just kind of like embedded into the positive charge. We know now that this model is not true, but this is what he came up with after he discovered the electron. Okay, so after J.J. Thomson discovered the electron, so this is our cathode ray tube. This is the positively charged end. The background screen lights up in the presence of matter, right? So they applied a voltage and they noticed that it traveled towards the positive region, meaning there had to be something negative in the atom. They didn't know that there was anything more than the atom than just an atom. Inside the atom now are negative particles, which are smaller than the atom themselves. So right after this, Millikan, okay, so now they have the electron. So right after this, Millikan determined the mass of an electron and the charge of an electron. He determined the mass to be really, 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 really small. Look at this, 10 to the negative 28. That's so tiny. So the majority of the mass of an atom can't be coming, most likely isn't coming from the electrons because this is so small. And then again, this is the charge, the actual charge of an individual single electron. In coulombs. Coulombs is a unit for charge, which we will talk about more second semester. I don't need you to memorize everything. I just need you to know the Millikan figured out the charge of an electron as well as its mass. And he did this by doing this oil drop experiment. It's kind of complicated. I'm going to show you a little video on it. If you don't fully understand it, I'm okay with that. Just know that he is credited with discovering the mass of the electron as well as its charge. Okay, so I'm going to show this YouTube video. So again, this is the 1900s. Now, I know that sounds like far away, right? But like I was born in the 1900s. Given it was the late 1900s, but it was the 1900s. Okay?
In 1909, Robert Millikan, working at the University of Chicago, succeeded in measuring the charge on the electron. He allowed a fine spray of oil to settle through a hole into a chamber where he could observe their fall. The top and bottom of the chamber consisted of electrically charged plates. He introduced a source of X-rays which can cause creation of charges when they strike matter. Charges produced by the X-rays attach to an oil droplet, producing one or more charges on the droplet. When there is no voltage applied, the fall of the droplets is determined by their mass and the viscosity of air through which they fall. When a voltage is applied, the droplets that have a negative charge will fall more slowly, stop falling, or even rise, depending on the number of charges on them. By adjusting the applied voltage and observing the droplets both with voltage off and voltage on, Millikan was able to determine that the charges on the droplets were all multiples of a smallest value, 1.6 times 10 to the minus 19th coulombs. He took this to be the charge on a single electron.
All right, so again, he discovered the mass of the electron based on how quickly or slowly they fell, and then he applied voltages and could figure out their charge based on the plates presented inside the container. Okay, so again, a mass of electron, charge of electron. All right, kind of randomly thrown in here is radioactivity. I just need you to know the three types for now: alpha, beta, gamma. Alpha is positively charged particles. Beta is negatively charged particles, and gamma doesn't have charge. These are particles that are emitted from radioactive substances and given off. So alpha particles are really slow moving. They have pretty low energy. And like if you had alpha radiation traveling towards you, if you held up a piece of paper, it wouldn't get to you. It's not very harmful. Okay, beta is a little bit faster moving, and it can get through paper, but it wouldn't be able to like penetrate your skin or anything. It can't get into metals. Now, gamma radiation is the worst. It's the gnarliest, right? Gamma radiation is super high energy. It moves super fast, and it can travel through several layers of lead. So we know there are certain radioactive substances like uranium that gives off gamma radiation, and people have used it in like chemical warfare, right? Because the gamma radiation is such high radiation that it can travel and penetrate through your skin and damage your organs and essentially kill you, really. So gamma radiation is super high energy radiation and super harmful, being given off from certain radioactive isotopes. Okay, this is just to show you how they know the charges of them. So alpha rays are positive, beta rays are negative, and then gamma rays don't have a charge. And they did this by putting some sort of radioactive substance in here, right? And they put it in a huge lead block so that it wouldn't seep out anywhere else. And then it traveled through, and then it came into contact. It went through two different plates, a positive plate and a negative plate. Now you notice that the beta rays start to bend up and hit the screen where it lights up, okay, at the top part. The reason it does that is because beta must be negatively charged, so you can see that it's attracted or trying to move towards the positively charged plate. And then the same is true for the alpha rays. However, alpha rays are determined to be positive. You can see them because it's trying to bend towards the negative plate and be attracted to it. Whereas gamma rays didn't seem to have a charge. It wasn't affected, attracted, or repelled by either of these plates. So it was assumed to have, or it is determined that it doesn't have any sort of charge. It's just super high energy. Okay. All right. Now, this is huge. So 1911, still 1900s. This was not that long ago. Again, I was born in the 1900s, the late 1900s, but the 1900s. So Ernest Rutherford legit found the nucleus. He discovered the nucleus, and he realized, okay, the nucleus not only is positively charged, it has all of the mass in it, and that the atom is mostly empty space where the electrons are, and that there must be positive charge in a very, very small center region of the nucleus. Now, I want to make this clear. He didn't discover protons yet. He just knew there was a positively charged like nucleus of an atom. Protons and neutrons were discovered later. Protons were discovered first, and neutrons were discovered later. Okay, so he did what was called the gold foil experiment. Now, I'm going to show you what he did, and then I'll go to the slide also to show. What he did was he took this gold foil. Now, the plum pudding model, let's say this is a gold atom, okay? See, I made it gold. The plum pudding model has all of this positive region, right, in his model. This is the wrong model. So the plum pudding model is like this, and then you have like electrons just kind of like embedded in here, okay? Kind of looks like a cookie, huh? Okay, so if all of this region right here was like so much positive charge, what he did was he took a substance that gave off alpha particles. Well, I just told you alpha particles are positively charged, right? And he shot the alpha particles at the atom. Now, if the atom was heavily positive pudding everywhere, positive particles and positive particles repel each other, meaning all of these atoms should have, or all of these alpha particles should have flown backwards because they should be hitting positive all of the time or a lot of the time if it's a pudding model. So they should, it would hit and be repelled backwards. Well, that isn't what happened in the gold foil experiment though. What happened is that they had the gold foil, which is just a bunch of gold atoms sitting here, and they had a fluorescent screen so they could see when and where the alpha particles were hitting. And the most of these alpha positively charged particles were passing straight through. And they're like, oh no, so why is it passing straight through? Well, if alpha particles are positive and they're able to pass straight through, the positive region of the atom must be really, really, really tiny. It isn't this big pudding of positive. It's a tiny region. And so then he discovered the nucleus was this tiny region. In the video I'm about to show you, she's going to say the nucleus was small but massive because the particles are heavily deflected, meaning the whatever's in the center is more massive than the alpha particles, which is why they're able to be deflected, as well as the fact that it's positively charged, it gets deflected. But she's going to say small but massive in the nucleus, and I know that sounds kind of contradictory, but what she means by massive is she means that the majority of the mass of the atom is in the nucleus. It's not going to be in the electrons. So the protons and neutrons are where the mass is heavily carried. So I'm going to go back and show you this video. This is I feel like this video does a very great job of explaining Rutherford's gold foil experiment. So I'll put this on for you.
In 1910, Rutherford and his co-workers were studying the angles at which alpha particles were scattered as they passed through a thin gold foil. Most of the alpha particles passed through undeflected. However, a few were found to be scattered at large angles, some even back in the direction from which they had come. This meant that they had collided with an object much more massive than the alpha particles themselves, yet so small that only a few alpha particles encountered them. This atomic level view shows what is happening. Most of the atom is occupied by the low mass electrons. The nucleus is small and massive. When an alpha particle encounters a nucleus, it is scattered at a large angle.
All right. So hopefully that helps you understand that he discovered the nucleus, which is huge to science, the discovery of the nucleus, and it's still what we use now. He just hadn't discovered the subatomic particles of protons and neutrons. Those were discovered a little bit later, but his experiment was key in the science field. So this should be prior knowledge. However, if it's not, we're going to go over it. So speaking of isotopes and radioactive substances, let's start practicing. I want you to try to fill in these blanks: the mass number, atomic number, protons, electrons, neutrons. Remember that all atoms of a given element are not identical. Dalton proposed that, but it ended up being proved wrong because they discovered some carbon atoms had more mass than other carbon atoms, for example. There's carbon 12, there's carbon 14. So let's go ahead and fill this all out. So the top number is the mass number. The mass number contains protons and neutrons because those are what most of the atom, or all of the mass of the atom is made out of. Electrons mass, they have mass, but it's considered negligible relative to protons and neutrons. So we almost call it, we will call it zero in terms of the electron's mass. It isn't really zero, but you saw that number. It was like 10 to the negative 28 or something crazy like that. So mass number 14, it's right here. This is an isotope. Atomic number 6. protons, 6. The atomic number and the number of protons are always the same. They mean the same thing, okay? If you don't see a charge anywhere, like +2 or anything, you're going to assume this is neutral, that this isotope is neutral. And in order to be neutral, you have to have the same number of positive charges as you do negative charges. So if there are 6 positive charges, you need 6 negative charges. The electrons and protons will match. Again, so if this is the mass number, this is protons plus neutrons. Okay, I put P plus because protons are positive. I put N0 because neutrons are negative. Well, I just need to get rid of my protons, right? And then I'll have the neutrons. I'll be left with just the neutrons. So 14 minus 6 is 8. Okay. So here we go. Let's do some practice. This right here is a different style of writing out isotopes. This does not say gold -197. It's gold -197. This number right here is your mass number. So what you will have to do is you'd have to go on your periodic table and find gold. And so gold, its symbol is AU. If you found it on your periodic table, I'll pull one up real quick in a second. If you found it on your periodic table, what atomic number is it? Anyone want to shout it out?
79.
79. Yes, good job. So that's also its number of protons, because remember, atomic number and number of protons are the same. Okay. Sorry, I'm going back. So 79, so that number would go down here, and then 197 goes up here. So protons is 79. Electrons, I don't see a charge or a charge mentioned, so electrons should be the same as the protons. 79 positive charges will be canceled out by 79 negative charges. And then neutrons is you take the mass number and you subtract the number of protons, and you get, it's 118, I think. Okay? So again, this is just a different style. So this is one style of writing out isotopes. This is a different style of writing out isotopes. Okay? All right, so let's try this. Magnesium has 3 different isotopes with a mass 24, 25, 26. I want you to write the symbol for each, and then I want you just to determine neutrons in the isotope. So I'll do the first one with you. So when I say the symbol, I want the magnesium symbol. Mass number goes up top. Atomic number goes on the bottom, so you have to go to your periodic table. You have to find magnesium. It's atomic number 12, okay? So this is 24 protons and neutrons minus 12 protons gives you 12 neutrons. So we just did the first one. So go ahead and do the rest. Are we good? So 13 for magnesium 25, 13 neutrons, and then 14 for magnesium 26. Hopefully this isn't too bad. Okay, so if you look at the periodic table, you'll notice that most of the numbers aren't like beautiful whole numbers. So like carbon is 12.01 and hydrogen is 1.01. Let's see, what's magnesium? Magnesium is 20. Oh, I guess it doesn't have its number. That's cool. Cool stuff. 24 something, I think. So the question is why are they not perfect numbers? Does anybody know? Would you like to unmute yourself and let me know?
Because they're averages?
They're averages of what?
The isotopes mass.
Isotopes, okay? So what scientists do is they take like a sample of carbon and then they analyze it and figure out how much of it is carbon 12, how much of it is carbon 14, how much of it is carbon whatever the other one is, 11 or 13. And then they average it. Now, it's very apparent, so there's 3 isotopes for carbon, right? If the average on your periodic table says 12.01, that's really close to 12, meaning carbon 12 is the most abundant carbon in a sample of carbon. It's wildly more abundant than any of the others because that number is so close to 12. Okay, and it's not that the others don't exist, they just don't exist in as big of proportions as carbon 12 does. So percent abundance is what we're going to talk about next. This is calculating, I'd like you to change this, I'm going to change it later, to average atomic mass. I like the word average in front of it. Again, this number comes from your periodic table. Okay, and the average atomic mass, what scientists do, like I said, is they take a sample of some substance, carbon, lithium, chlorine, fluorine, gold, whatever, and they take this symbol means sum, that means you're adding, of the isotope mass, which is given usually, multiplied by the percent abundance in decimal form. So in decimal form means you take the percent and you divide by 100. Because percent means per 100, aka you move the decimal 2 to the left of the percentage, okay? And then if there's more than one isotope, you do that again for the next isotope, and then you add them all together. So we're going to do a practice problem. It says naturally occurring chlorine is 75.78% of chlorine 35. Now look, this is its true average atomic mass. This is its true atomic mass unit. The reason they write chlorine 35 instead of chlorine 34.969 is because they're lazy. They're just not going to do that. 34.969 rounds to 35, so they call it 35. But this is its true, full, more accurate mass, okay? And then this much of chlorine 37. Okay, look, this number is super close to 37. So then you go, well, why do I have to do this? I can just go look on the periodic table and find the average atomic mass. You're right, but you should know how to do this math, and you have to know how to do this math because it will be tested to show your work. So here we go. Isotope mass. Let's do the first isotope, chlorine 35. Its true mass is 34.969 multiplied by, right here, percent abundance in decimal form, so 0.7578. So there's one. So here's where the sum comes in. Plus, there's another isotope, so we have to account for it. 36.966 times its percent abundance is 24.22%, also known as 0.2422. Okay, these two numbers add up to what? Anybody? These two percentages right here add up to what?
100. Add up to 1.
No. These guys add up to 1. These guys add up to 100. Okay, so in here we're using it's out of 1 technically instead of out of 100. So calculate that out. I'm going to give you a second. Calculate it out on your calculator. So this number times this number plus this number times this number.
35.45.
Perfect. That's what I got too. Now go find chlorine. Guess what it says on the periodic table? What does it say on the periodic table, guys? 35.45, right? This is how they do it. They determine these numbers experimentally, and then that's how they throw this number onto the periodic table. Okay? So, next. If chlorine has, we're going to talk about chlorine a couple more times today. If chlorine has 2 isotopes, chlorine 35 and chlorine 37, what is the percent abundance of the 2 isotopes? Okay? So, again, I want this to be average atomic mass. Again, this comes from the periodic table. or that's periodic table number. And then this is our equation. So you go, okay, well now I want to know this guy. Okay, last problem we were calculating this guy. So in order to know this one, you have to have this and you have to have this. So in this case, you would look up the average atomic mass on the periodic table and fill that in that spot, okay? And then again, we do have the isotope mass, right? We have this guy's mass. Notice they didn't use those beautiful long numbers, so we're not going to use the beautiful long numbers ourselves either, okay? So here we go. What is the atomic mass of chlorine, the average atomic mass? Well, you look it up on the periodic table. It's 35.45 equals isotope mass. So I'm going to do chlorine 35 first. Now, percent abundance is what we're solving for. So when we have an unknown variable, what do we generally call it in math?
Variable.
Yep. What symbol do we give it, or what letter?
X.
Usually X, okay? You could put Y, Z, I don't care what you put, but usually X, okay? So 35 times we don't know. Plus, right, there's two isotopes, so this is isotope 1. Isotope 2 is chlorine 37. Now, this is where it gets tricky. So if X is 35, this guy should be the rest. Now, how do we represent the rest?
1 minus X?
Yes, 1 minus X. So let's talk about this. Let's pretend chlorine 35 was 40%. You would not have written 40 here, okay? You would have written 0.4, right? We're doing decimal form, which means if this guy is 40%, this guy should be 60%, right? So guess what 1 minus 0.4 is? 0.6, which is 60%. It's a lot of kids want to do 100 minus X, but remember we're not doing decimals in here. We're not doing percentages, we're doing decimals. So 100% divided by 100 is 1 minus X, the rest, okay? So I'm going to undo this now. Oops. All right, so go ahead and do the math. You have to factor this out. This will be distributed in here, okay? So 35.45. I want you guys to work on this. I'm also going to work on it. 35x plus 37. Oops, that's not plus, it's minus 37x. This is a minus right here. So I'm going to move the 37 to the other side. And then I'm going to combine my like terms. This is 35x. This is negative 37x, negative 2x equals so I got 0.775 for x. We good? The negatives cancel each other out, right? Okay, so that's chlorine 35, right? We designated X to be chlorine 35. So chlorine 35 is 0.775. Now percentage-wise, that's 77.5% abundance, okay? So then you go, okay, well, you can very easily do chlorine 37 because chlorine 37 is just the rest. So I'm going to do it. I know you guys can just take this number and subtract it from 100, but I'm going to do it the mathematical way just to prove to you. Chlorine 37 is 1 minus X. So 1 minus X is 0.775. And you end up with 0.225. So that is 22.5%. And again, this adds up to 100. Any questions before I move on?
Do you use the remaining?
What was that?
Did you use the remaining number to calculate for chlorine 37?
I did. I used the 1 minus X to do it, but you could easily have just done 100 minus 77.5, right? Because whatever this is, the chlorine 37 should be the rest. Either way works. I showed you the longer way. I plugged in the 1 minus X, and it was 0.225, and then I turned it into a percentage. Either way is acceptable.
Thank you.
You're welcome. All right. All right, mass spectrometry, it's actually very complicated. They take and heat, this is how they check out different substances. They take and they heat them up. They're ionized and put through a magnetic field. And then this is how they kind of like separate out the heavier or less or lighter isotopes from each other. And then it gets determined on a graph. So I don't need you to know this part so much, but you are going to need to know how to read this graph. Okay, so because I wish I could move this. Okay, I don't know how to move my screen, but I'm sure you can see it full on your screen. So we've been talking about chlorine a lot. Chlorine has 2 isotopes, one with a mass of 35 and one with a mass of 37. Okay, and you go, okay, so this is called the mass spectrometry or mass spectrum. So this right here is pretty much percent abundance. Okay, meaning what percentage of it is each mass, and then the y-axis or the x-axis is mass number. So you'll notice that this guy is chlorine 35. If you look at 30, 31, 32, 33, 34, 35 for this peak. And then 35, 36 is blank, and then 37. So this is chlorine 35, and this is chlorine 37. Okay? It is very apparent that chlorine 35 is more abundant in a sample of chlorine than chlorine 37. They didn't get as much of it out. Okay? And we do know that. The last problem told us it was like 77.5-ish% chlorine based on those numbers. All right? So the question becomes okay, well, if chlorine only has 2 isotopes, 35, 37, how come what are these guys doing on here? If it only has 2 isotopes, why do we see more than 2 lines? Something's going on. Does anybody know what it is? What's something that you know about chlorine? It's a what?
It's a diatomic.
Yes. So sometimes chlorine doesn't like to be by itself, and it will bond to itself, meaning you can take 2 of these chlorines and combine them. So let's say you do a chlorine 35 and another chlorine 35. It's going to equal diatomic chlorine with a mass number of what? 70. 35 plus 35 is 70. Okay? Sorry, that's not a 6, that's a 0. All right? So then you go, well, how do you get 72? Well, that would be like the combination of a chlorine 35 and a chlorine 37. So diatomic chlorine with a mass number of 72. And then, well, what about 74? Where does 74 come from? Sorry, I'm kind of running out of room. But that would be like chlorine 37 and chlorine 37, making diatomic chlorine. 37 plus 37 is 74. Now notice that the most common one is definitely the one with both chlorines being the same of atomic 35. This should make sense too, because the average atomic mass on the periodic table is 35.45. Very heavily leaning towards the 35 and not the 37. Okay, so this is how you read a mass spectrum. How high it is how abundant it is, and the y-axis is its mass number, protons plus neutrons. Okay, now notice this next one is the same exact thing, but what they did instead is they used bars. Okay, it's the same thing as a line. Sorry about that, as a line. They're just using thicker lines. Okay, so I don't want the formatting to throw you off. So again, this is the same thing. So instead of giving you a word problem like we've been doing, they're going to give you a graph, and they're going to have you use data to calculate the average atomic mass. So it says use the mass spectra below to find the average atomic mass of the element in question let's just say question, and identify the element, the exact mass values. So here's our masses, or this number and this number. And then, so you go, okay, well, average atomic mass is percent abundance times mass number. And there's two of them, so plus percent abundance times mass number. And they're asking you to calculate this guy. That's who we want to find out. Oops, sorry about that. Calculate this guy. Okay, so you go, okay, I have masses. They're right here. Where do my percent abundances come from? Anyone? The graph, right? How tall this is its percent abundance. This is percent abundance. Okay, so 75.78% is what this is saying. 24.22%. So those are our percent abundance of mass number 37, and this is our percent abundance of mass number 35. You go, oh, but this doesn't say 35 and 37. Well, I know, but this is 35, right? 34.969 is going to be the isotope 35. That's so close to that number. 36.966, that's this guy right here. Okay, this number is so close to this guy. So this is plug and chug. So let's see, 34.969 times its percent abundance for 35 is 0.7578 plus this guy, 37. So 36.966, sorry, I kind of ran out of room, times its percent abundance is 24.22. That's how tall it is, 0.2422. So you calculate that out. I'll give you a second. You guys probably already know who it is, but I'm going to prove it to you. This would be why you say, well, why can't I just look it up? Well, I didn't tell you who the substance was. So you wouldn't be able to just look it up. You got to do the math. And what do you guys get?
35.45.
Okay, 35.45. And they ask you who this is. So you go on your periodic table because it says who the element in question. Identify it. So you go to your periodic table and you find out who has an average atomic mass of 35.45. Chlorine does. So that's who it is. Any questions before I move on? Okay. All right. So this is another mass spec problem. So it says the mass spectrometry of silver was vaporized, that means heated up, turned into a gas, injected into the machine. The data was plotted. It says find the mass value of, or it says the mass value of silver 109 is 108.90476. Okay, this is its really beautiful, accurate number as opposed to just chopping it off and making it 109. So they want to find the mass of silver 107. So what this is saying is you don't get to just write 107. Yes, I realize that's the mass number. They want the beautiful number. That's what they're going for. Okay, so let's work on this. Oops, sorry about that. All right, up here I'm going to write average atomic mass. Equals percent abundance times mass plus percent abundance times mass. And I do it like this because there's two isotopes, right? It's clearly showing two, so 1, 2, the sum of them. And you go, okay, so what do I have? What are these guys? Someone shout it out. What are these guys? Right here.
Percentages?
Percent abundance, perfect. These are so 107 is 51.84% abundance and 109 is 48.6. Now, just real quick, well, actually, we'll get back to this. Okay, so you go, okay, I have percent abundances, so I have these numbers. And then I also have one of my masses. I have the mass for silver 109, one of my masses. So I'm trying to figure out this guy. So then you go, well, what about this? Does anybody know what I do about this? Did they tell you who the substance was? Yes. So you look up silver on your periodic table and you plug it in right here. This number comes from the periodic table. Okay, so what is it on the periodic table? I think it's 107.9, is that right? Equals percent abundance. Let's do this guy first. So this mass is 107. That's the one we're trying to find, right? X, I don't know. And this guy's percent abundance is 0.5184 plus. Okay, we're on to the next guy. That guy's mass is 108.90476. Sorry about that. Times its percent abundance is 0.4816. Okay, so again, you'd have to multiply this number, subtract it from this side, and then divide by 0.5184. I want to give you a minute to do that. I already have the answer up here. Okay, so I'm going to give you about a minute to do it. I want you to check your answer, and then I want to talk about something real quick. All right, are we good? Did we get this answer? So silver 107 right here, its really true beautiful number is 106.91. Hopefully you can see why they call it silver 107, because 106.91 rounds up to a nice 107. Okay, here's something I want to point out. This is pretty much 50-50-ish, right? It's like half 107, half 109. So notice that the average atomic mass is, right? So if you wanted, if it's half 107, half 109, where should you be at average, right? Just looking at it. Someone shout it out. If it's about 50-50, if half of it's 107 and half of it's 109, on average, it should be about what?
108.
108, right? Look at it. Look at its average atomic mass, 107.9. It pretty much reflects it's a good close to 50-50 proportion of each of them. Okay, a little bit closer to 107, or I'm sorry, a little bit lower because you have a little bit more 107 instead of 109. It doesn't quite get to the 108. Okay, all right, here we go. So what's the difference between an isotope and an ion? Well, an isotope differs in the number of neutrons. That's the thing you mess with, and that's what changes the mass number. Messing with the neutrons changes the mass. You're not allowed to mess with protons. If you mess with protons, you change who the substance is. So the only way you can change mass of an atom is by changing the number of neutrons, and you create isotopes. Ions, however, are atoms that differ. So these are things that have charge, plus or minus charge. And the way you change charge is also, is electrons. Yes, protons are positively charged, but if you change protons, you change who the element is. So you can't change protons if you want to change charge of the same element. So let's go ahead and kind of do these ions now. So magnesium, number of protons, you have to go find it on the periodic table. It's atomic number 12, so it should be 12. How many neutrons? It is, I want to erase this. Hold on one second. All right. Neutrons. So this guy is your mass number, 24. This is protons, 12. So neutrons should be 12. Okay. And then you go, okay, how many electrons? Well, now I notice that this is not neutral. I see a charge here. Okay. So plus 2 means I've lost 2 electrons are negatively charged. So if you're becoming positive, it means you're losing electrons. If you're becoming negative, you're gaining electrons. So the easiest way to do this is go, okay, neutral neutral magnesium would have also had 12 electrons. That's what would have made it neutral, but it's not neutral, it's +2. I've lost 2 electrons to become +2. So if I lose 2 electrons, I'm only left with 10. Okay? Fluoride ion, number of protons. You go look it up on the periodic table. It's atomic number 9. How many neutrons? Well, I don't know. 19 minus 9 is 10. Okay? This is a -1. Well, neutral fluorine would have been 9 electrons, but it's -1, which means I have 1 extra electron. So instead of 9 electrons, now I have 10 electrons. Okay, so now we're going to use some terminology. Magnesium 2+ has the same number of electrons as which element on the periodic table? Well, here's magnesium. Okay, if magnesium loses 2 electrons, that's what +2 means. It has how many electrons? Well, 10, right? So who has 10? Well, neon does. So we would say magnesium is isoelectronic with neon. Okay, it's isoelectronic with neon because it has the same iso number of electrons. It isn't neon, it just has the same number of electrons as neon. So you go, well, why is this beneficial? Well, atoms tend to want to gain or lose electrons based on achieving stability, and we know our noble gases are super duper stable. So they will gain, lose, share, do whatever it takes to become stable and become isoelectronic with noble gases because noble gases are the most stable. A full valence shell of 8 electrons is considered stability. Okay, so let's look at F-, F-1. So you have fluorine right here. Okay, -1, I kept trying to, -1 would be gaining an electron. So you gain an electron, now you have 10 electrons. So F- is isoelectronic with, oh, sorry, who was that? I missed it. Neon again. Okay, so let's do a practice problem. I want you to throw gallium out. I don't even want you to consider gallium at all. We're going to pretend it's not even there. Okay, so the question is, are potassium, S2- and Cl- isoelectronic, meaning do they have the same number of electrons? And if they do, which noble gas are they isoelectronic with? So K+, S2- and Cl-. So K+, here's potassium. +1 means it's lost an electron to become 1 more positive. Well, if it loses electrons, it should have 19 to be neutral. If it loses 1, it has 18, so it would be isoelectronic with argon. S2- means sulfur has gained 2 electrons. Neutral sulfur has 16 electrons. 2 extra electrons means it has 18 electrons. Yes, isoelectronic with argon. Cl- has 17 electrons. If it gains -1, 1 electron, it has 18 electrons now, and they're all isoelectronic with argon. They don't turn into argon, they just achieve stability like argon. Okay.
So would that, I have a question.
Yeah.
Would that mean it would be more likely to bond with those two atoms? Like,
well,
they're isoelectronic with each other, wouldn't they would they be more likely to bond with each other?
the positive and negatives are going to be likely to bond with each other. Yes. That's what creates ionic compounds.
All right, thank you.
You're welcome. That's a great question. Okay. Now magnesium 2+ and calcium 2+, are these guys isoelectronic? Do these have the same number of electrons? So calcium +2 and magnesium +2. So magnesium neutral has 12 electrons. +2 means it's lost 2 electrons. So you go backwards, 1, 2. So it would be isoelectronic with neon. Calcium has +2 means it's going to lose 2 electrons. So it has 20 when it's neutral, so it has 18 when it's not. So it's isoelectronic with argon. So no, magnesium and calcium are not isoelectronic with each other. Magnesium is isoelectronic with neon and calcium is with argon, and those two aren't the same. They don't have the same number of electrons. Neon has 10, argon has 18. So no, those two ions are not isoelectronic with each other. Okay? Questions? All right. So if you have that blank periodic table, now is the time to get it out. I'm about to jam through it and then we will finish. So I'm not going to leave this slide on, but everything I talk about is going to, all the like words I say and families and stuff I talk about are going to be on this slide So we'll be labeling all of these onto the slide. So here we go. Here's my periodic table. Okay, as you can see, the majority of elements that exist in nature by themselves are metals. We have metals everywhere, so many metals. Only a very small portion are nonmetals. That's this top right area are nonmetals. And then this staircase right here, these are called your metalloids or your semi-metals. And they contain properties that are similar to some similarities to metals and some similarities to nonmetals. That's kind of why they're the divider. They kind of share both characteristics. So I'm about to color in this periodic table based on families, and we're going to go over some review that's going to help you to make sure you remember how to write formulas and such. So here we go. Family number 1. I'm going to leave out hydrogen because it's technically just over here because of the charge. Here's my first family. These are called your alkali metals. Alkali metals. Okay? They are the most reactive metals on Earth. They are super duper 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 reactive. The reason that is because they have 1 valence electron, and they really don't, they want to have, everything wants to have 8, right? So it really would like let's say sodium. Sodium has 1, these all have 1 valence electron. Sodium would really like to get rid of that electron because if it does, it becomes isoelectronic with neon right here. And neon is stable. Now, if it does, and it forms a compound to become stable, if it loses 1 electron, what charge does this family become? This whole family. Anybody? They're all plus 1. Perfect. Okay. Next family. These are your alkaline earth metals. Alkaline earth metals. So alkaline earth metals. These guys have 2 valence electrons. They're reactive, but they're not as reactive as your alkali metal family. They have 2 valence electrons. They'd really like to lose 2 to become isoelectronic with a noble gas and achieve stability. So if we lose 2, what is their charge going to be? Plus 2. Okay? This will be their charge when they're in a compound, not when they're by themselves. When elements are just hanging out by themselves, they don't have any charge. This is what happens when or if they form within a compound. Okay? All right, this huge family right here. These are your transition metals. Okay, and it ends here. They don't have a set charge. You'd have to know who they are with to know their charge. So they're not going to follow our pattern that you're going to see. But again, they're transition metals. They're generally pretty stable. Think about it. Like you see copper, silver, platinum, zinc, gold. They make jewelry out of that. Generally pretty stable. But these are your transition metals. They don't have a set charge. All of them are all different. Okay? All right, the next family I'm going to do are my halogens. That's this whole family right here. Halogens. Okay, now these guys have 7 valence electrons and everybody wants 8, right? Well, almost everybody wants 8. All they need is 1 more electron to jump over and be isoelectronic with a noble gas. They just need 1. So like fluorine just wants 1 extra electron. So if it wants to add an electron or gain an electron, when it's in a compound, it becomes -1. Okay, these guys are your noble gases. Okay, noble gases. They don't have any charge. Noble gases. Noble gases. Sorry, I can't. Okay. These guys down here. Let's do brown. This row. So if you want to try to remember, I just think of Los Angeles. L on the top, A on the bottom. LA. It's LA down here. Okay. So this top part are called your lanthanides. You can see that right here. Lanthanides. They're they're metals. They're all metals, and they're very similar to your alkaline earth metals in terms of reactivity. They're reactive, but they're not like crazy reactive like your alkaline metals. And then the bottom, have I done this blue? Series down here are called your actinides. Okay, and it says actinide right here. They're called your actinides. These are all radioactive, hence the word actinides. Okay. Now, these are the families that I care the most about. I will kind of circle a few things. So you go, well, what about these guys? Like right here. These guys are considered other metals. They're metals, they're just not part of any of these special named families. Okay. And then you go, well, what about these guys up here? Well, these guys are just considered other metals, other non-metals. So they're non-metals, but they don't have like a special family name, which brings me back to something I totally forgot to tell you. Alkali metals are the most reactive metals on the table because they have one valence electron. And your halogens are the most reactive non-metals because they only need one. So they'll like do whatever it takes to try to yank and bring in an electron. So they're super duper duper reactive. Halogens are super duper duper reactive non-metals. Okay. Now I want to kind of go back. I'm going to get rid of that black stuff. So, oh, and then your staircase, right? I'll keep it purple. These are your metalloids. Metalloids. This is in between metals and non-metals. They like literally divide the periodic table. They're your metalloids. Okay. Now I want to finish. What I'm going to finish up with is identifying the pattern on the periodic table in terms of in terms of charges. This is +1, +2. Okay, so you look at boron. This whole family right here, this entire family has 3 valence electrons. So it has the option. It can either go backwards 3 to get to a noble gas, or it could jump forward 5 times. Well, it's easier to go backwards 3 spaces than it is to jump forward 5 spaces. So boron and this whole family right here would like to lose 3 electrons. And if it does, what happens when you're losing electrons? You become positive or negative? Anybody?
Positive.
Positive. And how many are we jumping backwards? So you go 1, 2, 3. So this is +3. This whole family's charge when it's in a compound tends to be +3. So carbon is your middle guy. You don't see carbon often in ionic compounds. Ionic ones are the ones that have charge, mostly because it really likes to share electrons instead of transfer them. So this is our like cutoff point, ±4, because it could jump forward 4 or it could go backwards 4. It's just as easy to do both, right? So then we get to the nitrogen family, and nitrogen has 5 valence electrons. So it can either go 1, 2, 3, 4, 5 backwards to get to helium, or it could go 1, 2, 3 to get to neon. So what do you think is easier? Well, going forward 3 spots is easier. So it would like to gain 3 electrons to achieve stability. So gaining 3 electrons gives you a -3 charge. Oxygen has 6 valence electrons. So it either has to lose all 6 of them, or it could hop over 2 spots to the right. So this whole family, they'd rather gain 2 electrons because it only takes 2 steps to hop. Gaining 2 electrons is -2. So you should see the pattern. +1, +2, +3, middle of the road. -3, -2, -1. And then again, noble gases don't have any sort of charge. So this helps you when you're writing out chemical formulas, is knowing the charges of each family. And again, there's nothing you can say about charges down here. You have to have additional information. They don't follow a pattern in your transition metal area. Okay. That's it for me today. Does anybody, let's see, I'm going to stop screen sharing.